Okay, you guys, we're starting 10.2 Igneous Rock. When we're done, you're going to be able to say this. You're going to say, I can describe the cooling rate of magma and lava and the effects on texture of igneous rock. You're going to be able to say, I can classify igneous rocks according to their mineral composition. And then you're going to be able to describe the number of identifiable igneous rock structures. Now, we're not going to get through all this in this session, but we'll get through a good part of it, and we'll have a part 2 to 10.2, so it'll be 10.2 part 2. Okay, here we go. The first thing is you need to understand if we're looking at igneous rock. Igneous rock is that we have two basic types: intrusive and extrusive igneous rock. Now, here's the thing. It's really easy to understand when you think about the word in. By the way, you know, when you do definitions and stuff like that, you can't use the same word in the definition. So the definition of in, well, it's kind of hard to come up with a definition of in. On the interior, well, that has in it, right? So it's just something to think about. But when we talk about intrusive, it means on the inside, it cools very slowly. Why? Because your earth is an insulator, right? Makes sense, right? So we have magma that's in the ground and surrounded by all this other dirt and rock and whatnot. It cools very slowly. And so we have large crystals forming. Why? Because they're able to grow and grow and grow and grow and grow and grow, and they're not being shut off by being cold. Right? So intrusive igneous rock. Large crystals because it's cooling very slowly. Okay? Extrusive igneous rock. Extrusive. X is outside. Inside, intrusive. Outside, extrusive. So here's my thing. When we have family get-togethers at my house, right, we cook a lot. When we get done cooking and we get done eating, what do you do? Because there's not enough refrigerator space, what do? You set it outside, right? Wintertime, it stays cold. As long as the dog doesn't get into it, you're good, right? And so once that rock, that molten magma reaches the air, becomes lava, right? That's when it becomes lava. And it goes into the air has no insulating powers like the ground, right? So air is an insulator, but not that good of one with regards to something like lava. So lava's in the air, it cools down very quickly. We call this extrusive igneous rock, and it forms very large crystals. Very large crystals. Now, I showed you this video clip in the other session in 10.1, but I'm wanting to show it again just for a second to point out a couple of things. So let me start this over again. Boom. So when you look at this picture right here, this area right here is very orange. Can you see that okay? Very orange. This area over here, not so orange. It's like darkish, right? And so if you remember when we talked about stars, the brighter, the whiter or the bluer the star, it meant what? It was hotter. That's right. Yeah. It was more hot. It was hotter, right? Well, same thing here. When it comes right out of the volcano, it's hot. But look at these pieces. They're immediately cooling. That's why they're dark, right? And so the temperature is dropping immediately. This is extrusive igneous rock. It is dropping very quickly, and that's what's happening, right? So extrusive igneous rock.
A few hundred years ago, scientists believed that volcanoes were burning mountains of fire.
Right? And again,
today we know they're really openings or vents into the hot interior.
So here's a skylight. This is called a skylight. This skylight, if you look here, it's as orange as can be. Why? It's in the interior. It's being insulated. This outer piece right here that's on the edge, it's cooling off. Why? Because the air is hitting it. Now, this cooling off is still maybe 1,000 degrees, right? This is not something you want to put your tongue on, right? Down here, though, it's probably 3,500 degrees. It's very hot.
Of the planet.
Right? And so when we look at volcanoes,
around the world,
depending on the type of volcano,
nearly
if it's a flowing volcano, then it's probably going to produce more intrusive igneous rock on the surface than one that's an explosive volcano like here in the background right here. I want to show you this too. This is one of my favorite video clips. It's on lava bombs. Now, what this is a volcano that's erupting very quickly. And what's going to happen, would you hit the light over there, please? What's going to happen is you're going to see these people are not very smart. Okay? So we're on the rim of a volcano in a helicopter. And we're going to fly over, and there's some people here. And what you're going to see is the volcano erupts, and it's going to drop these lava bombs, and you'll see what a lava bomb is here real quick. And we'll talk about them. Look here. Oh. Look at these people. You're not smart. Look at it. Look how big these... One of those rocks hits them, and they're not having a good day. Now, we're going to talk about lava bombs a little bit later, but what I wanted to show you is this volcano erupted, and bits and pieces are cooling off very quickly. Oh, it's an airplane, not a helicopter. But bits and pieces, they cool off very quickly. Extrusive igneous rock. Look at these people. Here they are. I'm watching these things come down. It's like they get pummeled. Anyhow, so extrusive igneous rock. Good stuff. Okay, so everybody's good. So I'm going to show you this image. I love this image here. So in this image, we have magma. As it's going to the surface, it's cooling off a little bit. Intrusive igneous rock here in this little sill right here, or this magma pool. Intrusive igneous rock. Extrusive igneous rock out here, right, on the outside where the volcano has erupted. So again, real good diagram. Not very technical, but very good. All right. So what do we get when we have intrusive versus extrusive rock? Well, intrusive rock, because it takes a long time to cool, right, it is coarse grain. And I'm going to show you some examples. I've got some on slides that I've taken, or pictures that I've taken. And then, so intrusive igneous rock, real long cooling period, so that it gets really big crystals and well-developed ones, and so it becomes coarse grained. And that kind of looks like this. So this would be large crystals, and you can see it here. I mean, you can see the individual crystals here, and they grew. I mean, like it took a long time for those to slowly cool down. So that's intrusive igneous rock. Granite, like this tombstone back here. That tombstone, that is a very coarse grained. And what do I mean coarse? Coarse means it's rough. Means it's got a lot of texture to it. Intrusive versus extrusive. Extrusive igneous rock, right? It's fine grained, real thin grain, and I'll show you a couple of those. I had that big piece of pumice out back there, which is back in the corner right there. So big piece of pumice, real fine grain. Why? Because it comes out in the air and it immediately cools off very quickly, right? And so this is what this is bird poop here. This is not it, but this is fine grain right here. So again, basalt is what that was. Then you've got what I refer to as a tweener. Would you hit the light? So this particular example is porphyritic, and I've got a slide that I'm going to show you in about 2 minutes. But what you'll see, especially with this rock sample, is that we have crystals that are really small, and you have crystals that are really big. And so you can see what that looks like. So what happened here is you got a rock that cooled very quickly and bits and pieces that cooled very slow. It's kind of like the best of both worlds. And so what happens is there's two different crystal sizes, and it cools at different rates, right? And so if we look at what the crystals are, the big ones are phenocrysts, and the small ones are ground mass. But I want to show you a picture, so if you're watching this, this is the exact same picture of the rock that I've just handed around. And what do you have? Fine grain in the middle, and then the bigger, coarser crystals, porphyritic, right? Porphyritic. All right, I want to show you this little video clip. Could you hit the lights again? Now, this is a gal at the Colorado School of Mines. Why would Colorado be very good at understanding igneous rock?
Mountains.
Not just the mountains, no. It's a giant. What were you going to say?
I was going to say, is it a big crater?
It's a giant supervolcano waiting to explode. Colorado is. Think about it. Think about the geologic processes that are going on there. It really is. All right.
Hi, this is Jane Stammer from the Colorado School of Mines, and I'm here to answer your questions on how to identify an igneous rock. Igneous rocks are one of the three classifications of rocks. They are formed both below ground and above ground. When they are formed below ground, they're called intrusive rocks, and they are typically coarse-grained. When they are formed above ground, such as in a lava flow, as you would see in Hawaii, they're called extrusive rocks, and they're typically fine-grained. This is a basalt, which is an extrusive igneous rock. It is very fine-grained, and you can see there are little holes in here where air pockets once were. This is from an ancient lava flow in Colorado, and you can see these types of rocks all over the world, most notably in Hawaii and other island settings. Depending on the chemical compositions of igneous rocks, they can be both light in color and dark in color, and that is how to identify an igneous rock.
So, pretty simple what they're doing, and examples that we've talked about, easily understood. So it's pretty straight. This one's an interesting one. Again, cools very quickly. I've got a giant piece of obsidian back there that I'll pass around here in a minute. But what is it? It's volcanic glass. So why is it cooling very quickly? It cools quickly, and there are no crystals, virtually no crystals, and it's clear. And so this is silica and quartz that we see cooling at an incredible rate. It just makes glass. Okay, so when you're looking at these particular rocks, igneous rocks, you also look at color, right? Go ahead and hit the lights again. Matt, go ahead and hit the lights again, please. Yeah, thank you. All right, so I'm going to grab a couple rock samples here, and you'll see, and I've got pictures. Okay, so felsic. Felsic is light in color, and so The word felsic just means that it's high. And what would I write down here? I would write down that it's light in color because it's high in silica. Right? What's silica? Silica is sand. Now, this is a piece of obsidian. This is volcanic glass. And the first thing you're going to say, well, that's dark. Well, not really. It's just because it's thick. What can you see when you look through there? Can you see through there? Right through here?
Yeah.
You can see light, right? You can actually look all the way through this. Can you see through there? Right there. You see the light?
No,
Yeah. And so it's a piece of glass. And it's actually clear. And it's actually not very dark. So it's light. So this is felsic. But the key is that it's so thick that it's hard to see through it. But it is felsic. Okay? This piece of pumice right here. This would be felsic. It's white. Right? Well, gray. Wouldn't you say that's gray? Right? So that's gray. Right? It's light in color. Felsic. Intermediate. Now, intermediate's kind of a middle-grained color. And it's basically a medium color. And then again, this is less quartz involved. So the lightest one would be felsic with quartz. Not as much quartz for intermediate. But then you got mafic. But I want to show you felsic here. All right. So note in this picture, it's almost pink. Right? It's almost pink. This is felsic. Felsic. This rhyolite, again, it's almost pinkish color. It's felsic. Then you have mafic. Mafic is really dark. All right. So they're dark because they're rich in iron and magnesium. So this particular piece right here is mafic. This piece right here, which is, again, a piece of red lava, mafic, right? So it's not very hard to tell what they are. Don't worry about the white specks on there. That's not bird poop or anything like that. That's just snails that I found that in a tidal pool, and I grabbed it and took it home with me. And people have just took the snails off it. All right. So again, felsic, intermediate, mafic. Are we good? We good? We good? So here's a mafic gabbro. Look how dark that looks. And this is coarse grain. You can see the little white flecks in here. Here's a piece of basalt, mafic. Right? Basalt's mafic. It's dark. Okay. People who study volcanoes are volcanologists. And one of the things that they do is they go to great lengths to understand how volcanoes and how the processes of Earth work. So what I thought would be good is if we watch this little clip, it's only a couple minutes long, on volcanologists.
Most people wouldn't ask to be in a volcanic crater. But to a few men and women, it's a window into Earth's inner secrets.
There's nowhere I would rather be than standing on top of a volcano. You can almost sense the power and the smell in a lava lake when sound as well was exciting. I think it's just a really beautiful place.
I'm going to stop for a minute. I want to show you something. Look at how quickly this is cooling off. Red hot here, or orange hot, and it starts to cool off just seconds after it's left. That's how quickly extrusive igneous rock is happening, right? It's coming out, cooling off very quickly.
Beautiful place.
I guess I would say volcanologists are curious. You know, what we study is Mother Nature, and every time I go to Hawaii and watch the lava flowing, I remember why I'm doing this.
Being a volcanologist has obvious risks. It's one of the deadliest jobs in the world. When Mount Pinatubo in the Philippines threatened to erupt in 1991, nearly 75,000 people evacuated. Guess who stayed behind? A small team of volcanologists. Then the big one hit.
Yeah, I see that thing started going.
No, it's gone. I think my underwear is about 2.5 miles that way.
Pinatubo delivered the largest eruption Earth had seen in 80 years. Jim Morey was in charge of tracking the volcano's earthquake patterns.
Suddenly the two seismographs between the volcano and our observatory went dead, and some large flow was coming off the mountain towards us and had destroyed the seismographs. That was one of the times when I first began to think, you know, what am I really doing here?
A cloud of ash blocked the sun. A typhoon delivered torrential rains. The scientists knew they had to retreat.
They would just be pelted by cherry-sized rocks. It felt like, you know, the sky was coming down. There was a low roar in the background, which turned out to be this large Laharo mud flow that was going down a nearby river valley.
Jim and his associates were fortunate, but other volcanologists have not been so lucky. On May 18, 1980, David Johnston manned a geological observation post on a ridge 5 miles north of Mount St. Helens. The volcano had been swelling for weeks. It was ready to erupt at any time. But Johnston remained at his post. When Mount St. Helens exploded, rocks the size of refrigerators blasted his trailer. The debris raced by at several hundred miles an hour. David Johnston's body was never found. Dozens of other volcanologists have met similar fates in the past few decades.
They chose to live their life with these risks and experienced more than thousands and thousands of people in their whole lives put together because they were willing to take these risks.
So I think it's pretty cool that these guys do that. It's amazing what they do as a career. They're incredible, but it's also very dangerous. So, well, with that, what we'll do is we'll call it a day. I appreciate you guys have been great. You've listened and done a great job, and thanks very much. And we'll catch you on the next part B.